Alright, so in these next couple of examples, we're actually going to be looking at a couple different limits that initially don't look like L'Hopital's rule can actually be applied. But after we change the way these things look just a little bit, we actually will see that L'Hopital's rule does apply. In this first example, we're going to be looking at the limit as x goes off to infinity of this product, in this case, of x multiplied by a tangent of 1 over x. Well, if you think about this, as x is going to become gigantic, what's going to happen is that 1 over x is actually going to go off towards 0, because I'm going to take 1 divided by a massive number. In that case, that's going to get closer and closer to 0. What I'm going to then have is I'm going to have a tangent more or less evaluated at 0, which we know is going to then tend towards 0. But then at the exact same point in time, that x value is going to become larger and larger. So what the shape that this thing is going to be is it's going to be that first term's blowing up to infinity, where that second term is actually getting closer and closer to 0. So I'm in this situation that I have infinity multiplied by 0. And that's kind of a weird thing to think about. On one side, I'm going to have something becoming larger and larger. So my kind of gut intuition is going to say that my output should become larger and larger. But at the exact same point in time, I'm going to have something that's going to 0. And if I think about taking something and multiply it by 0, I should somehow have a 0 come out. So in this case, I have two different kind of worlds clashing. So it's in this kind of weird situation, but it's not a situation that can initially be handled by L'Hopital's rule. What I can do, though, is I'm going to change this thing from a product, and I'm going to make it look like a quotient. And that's going to set this thing up to actually be in a situation where it is, in fact, going to be a 0 divided by 0. So what's going to happen is that I'm going to still start with my initial limit. I'm going to have a limit as x goes off to infinity. I have my x multiplied by a tangent of 1 over x. What I'm going to do is I'm going to try to represent this thing actually as a quotient. Up on top, I'm going to leave this tangent of 1 over x alone. What I want to do is I want to take this little x and somehow bring it all the way down to this quotient. So what's going to happen is that I want to think about x, but I don't want to really think about it as being an x up on the numerator. What I want to do is I want to kind of undo this kind of reciprocal idea. It's this notion that if I have 1 divided by 1 over x, well, that's just equal to x. So what's going to happen is that that little x up on top, I'm going to bring it to the bottom of this expression, and it's going to come to the bottom as a 1 over x. So it's a really slick trick that I can actually take a product of two things and actually write it as a quotient. In general, what's happening is that if I have some a multiplied by some b, what's going to happen is that that b part becomes up on top, and then I can divide it by a 1 over a. So I can artificially make this product look like a quotient. And now you can see that the overall form of this thing is going to be something that's nice to work with. Just as we mentioned earlier, this 1 over x, that's going to get closer and closer to 0, and I know that tangent of 0 is getting closer and closer to 0. So what's going to happen is that my top part's going to tend to 0, and then that bottom part, well, by similar reasons, also going to go to 0. So I'm now in this situation that I can properly apply this L'Hopital's rule, because I'm in this classic indeterminate form of 0 divided by 0. What's going to happen is that when I differentiate everything, I will have to differentiate this 1 over x. I'm also going to have to apply a chain rule to this tangent of 1 over x. So let's think about what the derivative of 1 over x is going to be before we actually kind of dive too far into it. It's kind of good practice to remember some of these kind of early derivatives that we saw. The kind of bad way to go about differentiating 1 over x is using the quotient rule. The easier way to differentiate this thing is going to be to simply write this as an x raised to the negative 1. And then just use this power rule. What's going to happen is that negative 1 comes down, and you're going to have an x to the negative 2, which you could then write as a negative 1 over x squared. Like I said, you could have done that with the quotient rule. It sometimes just takes a few extra steps, but you get the exact same answer. If you wanted to test, you could do the bottom term, the low term, which is x, multiplied by the derivative of the top, which is 0 in this case, minus the top function, which is a 1, multiplied by the derivative of the bottom, which is going to be another 1, divided by this x squared, or that bottom part squared. So you do see you get the exact same step. It is sometimes nice to think about these classic reciprocal functions simply as just taking that exponent, making it negative, and then differentiating it using this power rule. In this case, what's going to happen is that I'm going to apply L'Hopital's rule. What I'm going to have is I'm going to have a limit as x goes off to infinity. Differentiating that tangent, I'm going to have to use a chain rule in this case. I know that the derivative of tangent is going to be a secant, in this case a secant squared. I'm going to evaluate that thing at the classic inside part of it, and then I'm going to multiply it by the derivative of the inside part, which in this case we just computed as a negative 1 over x squared. What's going to happen is that that whole thing is going to be divided by the derivative of the bottom part, which we also know as this negative 1 over x squared. In this case, actually, one of the kind of neat things that would have happened, I guess, is if you would have done that derivative wrong, as long as you did it wrong both steps, these two things you can see are actually going to be the exact same term, so they're going to simplify to make a 1. So what happens in this case is I end up with a limit as x goes off to infinity. I'm going to have a secant squared of 1 over x. That 1 over x term is going to go to 0 as my kind of x's become larger and larger. So the ultimate limit in this case is then going to become a secant squared of 0. I know that secant is going to just simply be the reciprocal of cosine, and cosine at 0 is going to be a 1. So this whole entire expression is going to become a 1, officially a 1 squared, which then just becomes a 1. So in this case, you had this situation that it was going to be this weird multiplication of something that's blowing up to infinity, multiplied by something that's getting closer and closer to 0. So it's this idea of who wins this battle. Does 0 win or does infinity win? In this case, you can see that they actually kind of blend each other out, or they smooth each other out. What ends up happening is that everything kind of simplifies off and you're left with a nice classic just whole number, in this case a 1.